So we're going to go ahead and get started with the water cycle budget equation, but before we do that, let's take a look at the system that we're going to be working with today. So this system, we're just going to think of this as sort of a forested ecosystem somewhere out in the beautiful Sawtooth Mountains in Idaho. And so we're going to draw a box around this forested ecosystem. It contains a range of different trees of different ages and different species. And our system is going to extend out into the atmosphere above the canopy, maybe just a little bit, but not too much. So maybe think of this as being maybe 5 or 10 meters above the tippy top of the canopy. Our system will extend into the soil beneath the roots of all of these plants and maybe into the weathered bedrock. And it's going to extend from side to side in a direction that captures a good range of variability of this ecosystem so that it's sort of representative. Now, one important thing is that we are going to assume that this system is isolated from its surroundings laterally. So all of the fluxes of water, energy, and carbon will either come in through the top or out through the top, or in from the bottom or out through the bottom. There's no exchanges of water, energy, or carbon with the sides, through the sides of our system here. So let's go ahead and start with the budget equation for water. So the storage term is going to be referred to as the Greek variable theta, which is going to stand for soil moisture. The amount of moisture in the soils, but also in the plants. The primary mechanism for water delivery into our system is through precipitation through the top. Water can also leave our system from the land out into the atmosphere through the evapotranspiration flux, ET. And if we're thinking about other fluxes, we have maybe some leakage of liquid water from the soil to the groundwater, which is R, recharge, as well as some runoff, which we will denote as Q. Okay, so now we can move on to the budget equation. So the change in storage, the change in soil moisture with respect to time, or the rate of change in soil moisture with respect to time, that's our change in storage variable, is equal to or balanced by input to our system in the form of precipitation, P, and there actually aren't any other inputs of water to our system. So we'll start with the outputs. We have outward going evapotranspiration, that's a loss of water from our terrestrial system to the atmosphere. We have another loss from the soil system to deeper groundwater, which is recharge. And then we have another loss from our terrestrial system in the form of discharge, which we denoted using the variable Q. So that's our budget equation for the conservation of water mass in our system. And it says that the change in soil moisture with respect to time is equal to precipitation coming in and the sum of evapotranspiration, runoff, and recharge leaving the system.